Hello, this is Will Langhorn, and in this video I'm going to be demonstrating a component of my final project for ENCE 205. This is a model I built in Fusion 360 that's intended to demonstrate the importance of stormwater management and stream restoration to high school students. This model is built out of parts that can be 3D printed or found at local hardware stores, so very easy to assemble and very cheap. Um, it's intended to be set up in an auditorium on a table like this, maybe in a classroom, somewhere where students can come up and interact with it. There are a lot of different parameters in this model that students can mess with, so it's intended to be very hands-on. Ideally, you'd also have this model set up next to a screen where you could play the PowerPoint presentation I've included along with the simulation. That PowerPoint just provides a little more detail about stream restoration. Um, and so this model is approximately 1 meter long by half a meter wide. So about a foot and a half by 3 feet, give or take a little bit. So the components of the model itself include on the left here, this is the water reservoir. This is where all the water that goes into the model comes from. In this design, it's an open top reservoir, so all of the water can be easily added using a bottle or some other container. This little black shape in here, that's intended to be a submerged pump. This is a pump that you can find for a small fountain or fish tank. They're available on Amazon for maybe 20 bucks. Coming out of the pump, you can see there's this gray wire up here that runs segments into four pipes, not wires, sorry, four pipes that flow that are across the top of the model. Might be easier to see from this angle. So the water flows through the pump into the pipe and across the model. And this gray pipe is intended to be perforated with little holes. So when water flows through it, you essentially create a mist that simulates rainfall over the model. These PVC pipes right here, these are just support structures. They're 1/2 inch PVC pipes. No water really flows through them. Down here, you can see the second outflow from the reservoir. This is again 1/2 inch PVC pipe with a valve here that you can open and close to varying degrees. And the water flowing through here is intended to simulate stream flow. So if you look at the model right here, you can see the water flows out of the reservoir into this box and into this modeled stream bed down here. And then at the far end of the model, this is on the right here, this is 3-inch PVC right here. This is intended to be the outflow from the model. So this is where all of the water from the rain system and the flow system will come out. And so ideally at the bottom here, you would have some kind of container to catch all the water, but you might also have a graduated cylinder, for example, and with that, students could measure the flow rate out of the model, so you could test how different stream designs in the model affect the velocity of the water coming out by measuring how quickly the cylinder fills up. You could also assess the turbidity of the water, how much sediment is being carried out of the model. By visually inspecting the water in the graduated cylinder, or you could even take a sample of it, as we've done in lab, and using a spectroscopy machine, get an idea of the absorbance and the turbidity. So the main component of the model is this stream bed system here, and to give a better view, I'll turn off the rest of the model. So this here is a model of a stream bed. On the top and bottom here in green, you can see this is a topography surrounding the stream. This is intended to be printed using a 3D printer. And then in the bottom here, this is essentially just sand that you would fill in. And this sand represents the floodplain of the stream. And the idea is that students could trace different stream patterns through the sand and then get an idea of how the stream patterns affect runoff. Now this model here comes from um, a section of Paint Branch Creek, actually. This is an image from PG County Atlas. As you can see here, the topography and these lines that are here and on the bottom. And then also in blue here and in orange, this is the floodplain of Paint Branch Creek in this section. So one of the reasons that I chose this section of Paint Branch Creek is because this it showcases a lot of different interesting land uses. On the bottom here, you can see it's very residential. There's what appears to be a sort of cul-de-sac down here, a road. You can see that there's a lot of different properties around here. So you'd expect to see a lot of impervious area here, a lot of structures. Whereas up here, you can see there's not very much property, not very many property lines segmenting it. And if you look at it on satellite view, you can see that this is primarily wooded area. So this area is likely to be very pervious as opposed to impervious down here. And you could model this, for example, in the model by maybe placing some kind of felt or absorbent fabric on the top section here to model the pervious nature of the woods. And then down here, you could leave the plastic bare so you'd have more runoff from the rain coming from this more residential area. And then another way that you could simulate differences between different land uses are using these little dye packets that I have here. So these are essentially dye in powdered form, these little discs, and when they mix with water from the rain system, dye would run off from these discs and into the water. So this little red disc right here, you could use that to simulate maybe nitrogen or phosphorus runoff from the lawns in the residential area, whereas this green dye up here, this dye disc, you could use that to represent biological contamination, maybe from fecal matter from wildlife that's living in that wooded area, or maybe even pets that maybe owners walk through that wooded area. So in this way, you could simulate nutrient pollution and different microbes that might flow into the water due to runoff, and then the students could obviously analyze how the dye concentrations look at the outflow at the end of the model. So a lot of the creativity of the model really comes into creating different channels through the floodplain. So you can see here I've traced a version that tends to follow the floodplain pretty well, but you could envision perhaps, let me zoom out, you can envision creating another model that's maybe a little more channelized, like this top one over here. So you can see in this version of the model here, the stream bed is a lot more rectangular. It's deep cut, it's very narrow. There's a lot of bends here. So you can imagine if students were to design this sort of stream bed representing more of a channelized flow, you'd expect to have more erosion, more sediment flowing out on the right here through the end. So this just really shows that students can they can use their fingers, they can use other utensils to kind of trace out different patterns. You might even consider eddies or pools in the stream bed. Lots of different ways to interact with it. You could even encourage students to bring in rocks or sticks that they could place in the stream bed that could act as little buffers, like boulders or trees might in a real stream. You could construct little engineered systems like the engineered vein that we saw in class on Paint Branch Creek that was intended to increase the amount of dissolved oxygen in the creek. So just ways of creating riffles, and there's just a lot of different things that you could add. You might put in um, like pervious, like foil channels would simulate maybe through a concrete channel, and you could analyze that that flow is different from flow. For a lot of creativity. So let me just bring these back. Summary, this model is designed to allow for a lot of creativity, a lot of hands-on learning. The water system allows you to simulate a bunch of different events. You can simulate high intensity, high duration storms, or you can simulate high intensity duration flows. You might simulate more dry season by reducing the flow into the system, the stream flow into the system. So there's a lot of different ways that students could take control of this model, could test out different things, see what works, see what reduces sediment, see what increases it, and then using this model, they'd get a better sense of how streams are restored in their neighborhoods or their communities. Um, it would give them just a very practical understanding. And they can go through the engineering process of designing and building all within the matter of a few minutes. Um, so I can, if I, as a student, as a high school student, if I had access to a model like this, I think this would really increase my interest in environmental engineering because of just how it would have allowed me to test out different things to really get a hands-on experience. So this is my final project. Thank you for watching this video.